Welcome back everyone to part 4 of text generation. In part 4 we're going to be focusing on creating the model. We'll start off by setting up a loss function and then we'll create the model. In this case it's going to be a pretty simple model, just 3 layers, an embedding layer, a gated recurrent unit layer, and a dense layer, 1 neuron per vocab character. Alright, let's head over to the notebook and continue where we left off. Alright, here we are at the notebook where we left off last time. I want to quickly get some variables out of the way. One is vocab size, which is just the length of the vocab list we made earlier. Essentially, how many characters or unique characters there are. There's 84. The next is the embedding dimension for our embedding layer. So this is something you can play around with. We're going to choose 64 since it's more or less in the same range as our total vocabulary size. You don't want to go too large on this, otherwise you'll start embedding to too many dimensions where some of the dimensions or features discovered there aren't going to be very useful. So you want to choose something at the same scale of your actual vocabulary size. And then we're going to just have a single layer. So in our layer we'll just choose a lot of neurons. So let's go ahead and choose 1026 or 1024. Doesn't really matter too much the details there. But we're going to choose just a single layer with a lot of neurons. This is something you can really play around with. You can choose multiple layers, and you can choose things like LSTM layers or gated recurrent unit layers, stack them on top of each other. You can add in dropout, but we're going to try to just create the simplest model that can produce realistic results. And in our case, that's just 3 layers. Okay, so let's create a function that is going to actually create a loss function for us. But to do that, I need to do a couple of imports first. We're going to say from TensorFlow.keras.losses import sparse categorical cross entropy. I'm just using tab for this. So because our labels are one hot encoded, we're going to need to use sparse categorical cross entropy. And you can check out our notebook. We have a link discussing the difference between sparse categorical cross entropy versus just categorical cross entropy in Keras. And if you want more details on this, you can just say help on this function, sparse categorical cross entropy, and it will show you that essentially this from logits is what we need to edit. So from logits, that essentially relates to whether or not you're one hot encoded. We are one hot encoded, so we need this to be true, which means we can't just pass in the string sparse categorical cross entropy. So what we're going to do is we're essentially going to wrap this. We'll say sparse cat loss, take in y true and y pred, just as this original function does. And then we're going to return sparse categorical cross entropy function with that y true and y pred. However, we'll specify that from logits is true. So that's the main reason why we have to create our own custom loss function here, because we need to specify this parameter to be true. And the reason we can't just pass in the default sparse categorical cross entropy is because the default there is false. So we'll see in a second when we actually pass in the loss why that happens to be the case. So let's create the model. We're going to do this through a function. That way, when you're dealing with your own vocabulary sets and your own text data sets, you can easily adapt this function to your own models. So this will take in the vocab size, the embedding dimensions, the number of neurons in the recurrent neural network layer, and then the batch size. All things you can edit. So we're functionalizing this again, kind of for repeatability. We'll create a sequential model, which means we actually have to import these. Let's go ahead and do that in a cell here. We'll, just as we always do, we'll import from TensorFlow.keras.models, import sequential, and then from TensorFlow.keras.losses, actually, whoops, from TensorFlow.keras.layers, import, and we'll be using an embedding layer, a gated recurrent, GRU, all caps, and then a dense layer. And you can play around with this. You can switch this out for an LSTM layer if you want. You can add in dropout layers, etc. Really up to you, but we'll use the simplest network possible that gives us realistic results. So now I can say model sequential, and let's add in those layers. So the first layer is going to be that embedding layer, which embeds this to some amount of dimensions. We'll say embedding go ahead and pass in the vocab size, so what the actual input is. If we do Shift Tab here, I'll tell you what is the actual input dimension expected. So the vocab size is the input dimension, and then that's going to be output to some embedding dimension. So embed dimension, and then the batch input shape. So if we take a look at this function and continue going down, it has these keyword arguments that you actually don't get to see. And one of them, if you end up looking at the documentation, is batch underscore input underscore shape. And the shape is just going to be batch size by none. Okay, so that's the embedding layer. Next, we're going to add in our gated recurrent unit layer, where we have the number of recurrent neural network neurons you can choose in this layer. And there's a couple things we're going to be showing you / playing around with. So if you expand on this, you'll notice it has a couple of parameters here that you can do. You can actually specify a dropout call within this layer, which is kind of nice. But the main thing we're going to be doing is we're going to say return sequences is equal to true, and we're also going to say that stateful is equal to true. And if you kind of scroll down and start reading about these, so first we'll show you return sequences. So this basically tells the layer whether or not it should return the last output in the output sequence or the full sequence. And we do need to return that since we're dealing with those sequences shifted over by one time step. We want to see that history. And then stateful, if it's true, which we are going to say it's true, then the last state for each sample at the index I in a batch is going to be used as the initial state for the sample of index I in the following batch. So we want it to keep that current state. Okay, so we'll go ahead and pass those in as true. So we'll say return sequences is true, and then put this in a new line, so save a little space. We'll say stateful is true. And the last thing we're also going to specify is the actual initializer of the weight values for our recurrent layer. And we can do this by saying recurrent underscore initializer is equal to, and there's several string codes you can pass in here. If you notice at the original signature of this function, it takes in the kernel initializer as Glorat uniform, but the recurrent initializer as orthogonal. So we're going to change, based off of just research in this topic, that the recurrent initializer typically performs better if it's set to the Glorat uniform as well. And Glorat is actually just the name of the person that developed this. His name is Xavier Glorat. So he has the first name Xavier, last name Glorat. So this is typically things are named after your last name if you're a researcher and you develop them. But for whatever reason, it's actually quite common that people just refer to this as Xavier initialization, which is actually the guy's first name. So it's kind of interesting. And at the time of this filming, he currently works at DeepMind. So he's very much still active in the space. All right. So finally, we're going to add in our dense layer. Easiest to understand because it's just the vocab size. Okay. So then we compile our model. We'll go ahead and compile it with the Atom Optimizer and then with our loss function. And for our loss function, we actually just pass in the function itself. We do not call the function. And because of the fact that we're not allowed to call the function inside of this compile call, that's the reason we had to essentially edit this function a little bit in order to specify from logits is equal to true. Because there's no way you could specify from logits equal to true if you're not allowed to actually call the original function, which by default has from logits equal to false. So that's why we're not able to just pass in sparse categorical cross entropy as a string here, because this from logits statement. Okay, once we're done with all that, we'll simply return the model. Go ahead and run that, and let's create the model. So we'll say model is equal to create model, the function we just made. The vocab size is equal to the vocab size that we just defined. The embedding dimension is equal to the embedding dimension variable we created. Recurrent number of neurons equal to recurrent number of neurons, and then batch size is equal to the batch size we specified earlier. So pretty much we've already made all these. Go ahead and run that, and then call for your model summary. And it should look something like this. So notice the shapes right here. Specifically, notice the batch shape. So the 128 is our current batch size. Later on, what we're going to do when we're training the model is we will actually change this upon reloading the model's weights to expect just a batch size of 1. So coming up next in step number 5, we're going to show you how to train the model. And we'll first make sure everything is okay with our model by actually running it without any training to just get a bunch of random characters. So we'll do that in the very next video. I'll see you there.